Let's look at a collision theory of reaction rates. Just having a collision isn't enough. You need to have the collision occur with the correct orientation. So molecules have different sides. They need to hit the correct side. They also need to collide with enough energy for the bonds to break. And it's important that you have no more than 2 molecules. The chances of 3 or more molecules lining up is near impossible. If you just think of the probability of the orientation and having to collide with just the right speed, it's impossible to have more than 2 molecules colliding. So let's look at the very first collision that we have here. So we see that it's an ineffective collision, and then looks at the second one. So the first molecule is rotated around, so now it's blue side first, and that is also an ineffective collision. The collision that works in this particular reaction is when that blue atom hits the edge of the ozone, and then you're able to get the NO2 and the oxygen. So again, this is called collision theory of reaction rates. So in your homework, you should have some sort of fill in the blank or some sort of question relating to these, but let's go through these different postulates of collision theory. So the rate of a chemical reaction depends on the concentration of the reactants. The more concentrated it is, then the more collisions you'll have, and therefore the faster the rate you'll have. The order of each reactant depends on the detailed reaction mechanism. So that means is how the orientation, how it's going to come and react. Is there a cascade of reactions to give you an overall reaction? C, changing the temperature, or if you use a catalyst, this will change that rate constant, K. So if you add a catalyst or if you increase the temperature, then that will increase the value of K, so give you a larger value rate law constant. The general rule of thumb is that a 10-degree temperature increase in temperature doubles the reaction rate. So they used to teach this more 20 years ago in the AP chemistry program. They've kind of moved away from this, but just so you know how rapidly the reaction rate can increase, just know just a little bit increase in temperature can cause that reaction rate to double in this case. E, the molecules must collide in order to react, but that's not all. They must collide with sufficient energy and with the correct orientation, the geometry, so that the collisions are effective. And just to put this into your mind again, the larger the K, the faster the reaction. Let's look at activation energy. We have talked about this before. So the activation energy is the minimum energy required to break the bonds and start the reaction. So this could be adding heat to the reaction, it could be friction, it could be sunlight, it could be a spark. So if you're thinking of a combustion reaction, to get the newspaper on fire, you have a spark or a flame to get it going. And again, that's called the activation energy. This right here is an exothermic reaction. So I see that my reactants are higher energy than my products, and here is that activation energy right here. At the top of that energy hill, this is a transition state or an activated complex. This is where the bonds are broken or reformed, and then you slide down the inner energy hill, releasing heat or releasing that energy because my products are formed. So this change in reactants to products, this is called the enthalpy, which we will talk about in a later unit. Again, when reactants over here are higher potential energy than products, this is an exothermic reaction, so you'll have energy leave in the form of heat. And in an endothermic reaction, it will pull in heat from the surroundings. My reactants have a lower potential energy and my products have a higher potential energy. Notice that in an endothermic reaction, the activation energy is a lot higher. These endothermic reactions tend to be less common than the exothermic, but they can still happen, especially if you are increasing the disorder. Here's just another picture of exothermic and endothermic. Again, most things that we see in the laboratory are exothermic, where energy is released. Let's look at energy diagrams. You might be asked to do some calculations with them. So on this, you just pay attention to what the potential energy is, and you add or subtract those values to be able to figure out how much the activation energy is, or how much heat is released into the atmosphere, how much heat is sucked in to the reaction. So we have two charts. We have 1 and we have 2. And let's look at the activation energy for the Ford reaction. So on the Ford reaction, activation energy, it starts with the reactants and then goes up to the top of the energy hill. So I start with 150 and I end with 200. And you always do final minus initial. So this takes 50 kilojoules per mole. And let's do the second one. So the second one, I start at 100 and I end at 400. So that would be 400 minus 100. So I get 300. So that's for the Ford reaction. We can also have the reverse reaction. So that would be starting with products and going to the reactants. So going backwards, so going this way, I start with products and I go to the top of that energy hill. So I'm going to have 200 minus 50. So that activation energy would be 150. And then let's do the reverse reaction here. So I start with products and I go up to the energy hill. So I have final minus initial, so 400. Final minus initial, so 400 minus 300. So that would be 100 was the activation energy for the reverse reaction. And then delta H, this is the enthalpy. So this is the difference of products and reactants. And you usually do products minus reactants. So on that first one, my products are 50 and my reactants are 150. So 50 minus 150, I'm going to get a negative 100. So this tells me that I have negative 100 kilojoules will be released to the atmosphere. And then on the second one, products minus reactants, I have 300 minus 100. So I have 200. So notice that in an exothermic reaction, you have that negative sign that tells you the direction that the heat is going and it is leaving the reaction or exiting the reaction. That's why it's a negative. While this endothermic here, it's positive. So that means that heat is being sucked into the reaction. So I have positive 200 kilojoules coming in. And on this one, I have a minus 100 kilojoules going out. You can't have negative energy. It's just showing, the negative sign is just showing the direction. How does temperature affect activation energy? Temperature equals the average kinetic energy of the molecules. If you increase the temperature, you increase the average kinetic energy. So that means the molecules have more collisions and more forceful collisions. So both those things happen, more collisions and more forceful collisions. The more energetic the molecules, the more energetic the collision. And this is a diagram that shows two different temperatures. And right here, this dotted line, this is your activation energy. So at some point, the collisions are going to be strong enough because there are more of them and also more energetic that the reaction is going to be able to occur. So that would be the activation energy that you could put on this graph. And then we see two different temperatures. You see that there's always a wide range of energy in the molecules. So some are going slower, some are going faster. But you see overall with the second temperature, you get more molecules that are able to achieve that activation energy. And reading this chart below the curve, I would have the same number of molecules. And you see with an increase in temperature, that curve flattens out a little bit. And you end up getting more molecules over that activation energy. So which temperature is greater? So this would be my second temperature. Which temperature has more molecules with enough energy to overcome the activation energy? That would be the second temperature. So you should be able to draw a graph such as this and put in the activation energy and show that this second temperature has more molecules that are able to react because they achieve that activation energy through more energetic collisions and more forceful collisions. This is another picture that's showing that activation energy. They're calling it a threshold energy. But you see with the higher temperature, it flattens out a little bit and you get all of these molecules that are able to react and form products. This is a picture that's just showing the potential energy diagram, activation energy, and put with the Maxwell-Boltzmann diagram that shows the two different temperatures. So that is your activation energy. So again, I can label the activation energy here, and I can also on this chart, it's turned on its side. That is the activation energy there. The Arrhenius equation used to be in the AP program, and they used to give it in your data sheet. It's a way to mathematically describe what is on this slide. They've taken away the equation, and instead you just need to know the concepts. So the rate law constant K, it changes with a temperature change and with a catalyst, but that's it. With a temperature change, if you increase the temperature, that gives you a larger rate law constant and therefore a larger rate. With a catalyst, it gives you a larger K and a larger rate. Without a catalyst, you would have a smaller rate law constant and a smaller rate. You should know this, that the rate law constant K does not change with different concentrations and with different pressures, and this is also a concentration. So if they change the pressure of something, this will not change your rate law constant. It's only if you change the temperature or if they say they add a catalyst. Large activation energies will have a small K and the rate will be low, and that's because it takes a lot to form that activated complex because it takes so much activation energy. Small activation energies will have a large K and then a high rate, and that's because it's easier to get over that energy hill to form that activated complex.